just like you started to form some rules in your mind for how to take derivatives, just like you formed some rules in your mind for how to simplify logarithms or to simplify exponents, we have some rules that can help us simplify expressions that contain definite integrals. If you like them in this form, that's fine. They all follow from this idea that a definite integral is just a fancy notation for adding up a bunch of areas, specifically the areas of infinitely many rectangles. But just think of this, all this means the integral from a to b of f of x dx, find the area under f of x between a and b. So things you know about area, you can split areas up into smaller pieces and add them up. You should get the original area back. Those all apply. So if you change the order of the limits on your integral, you have an opposite result. And what's going on there, this one could be hard to understand at first. Remember that the integral is a model for multiplying the heights of a bunch of rectangles times the width of every rectangle. Well, here, if I change my limits, if I change their order, I still have the exact same heights, but my widths are now negative. So if I told you that the integral from 2 to 5 of f of x dx equaled 3, then you would know that the integral from 5 to 2 of f of x dx equals negative 3. All right, the next property, if I have a lower limit that's equal to my upper limit, imagine what that picture would look like. Find the area under the curve f of x between a and a. So I could try to draw a rectangle there. I can't squeeze infinitely many rectangles in there, but any rectangle I tried to fit in would have a height of whatever f of x is, but would have a width of 0. So if I told you I wanted to know the integral from negative 3 to negative 3 of some crazy function g of x dx, you know, since the lower limit and the upper limit match, the result is 0. If the function that serves as your integrand has a constant multiplier in it, you can factor that multiplier out to the front. So just know what's happening there. My integral is really height times width plus 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 height times width for a bunch of rectangles, right, to find their areas and add them up. So you could think of that, since my width, in theory, is infinitely thin, but you can imagine factoring the width out to the front and having height plus height plus height plus height plus bump, bump, bump for infinitely many heights. So if all of a sudden you said, oh, hey, I'm going to make all those heights 3 times higher, what math could you do? Well, you would have 3h1 plus 3h2 plus 3h3 plus 3h4 plus dot, dot, dot. You just factor the 3 out to the front, which just means it's going to multiply your area by a factor of 3. So you could find the area of your original, under your original curve and multiply by 3, or you could find the area under the new curve. The two results will be equivalent. Next rule, sums and differences. Just remember how when you found the derivative of two functions added together, you just added together two derivatives and it was really, you're like, oh, I like that rule. It's easy. It's kind of, you don't even have to think about it. Same goes for adding up definite integrals. If you have an integral whose integrand is a sum, so two functions added together, you can separate that out into two separate integrals and find the areas separately and add them. Same goes with subtraction. You're really just having a constant multiplier of -1. Here's one more that is very powerful, sometimes forgotten. We call it additivity. So remember, definite integral means area under a curve between two input values. So the only time additivity ever works, you have to make 100% certain that the two integrals that you're thinking about have the exact same function as their integrand. So notice these two functions. That first integral says find the area under f between a and b. Here's a little picture. It's the part I just colored in. The next integral says add to that the area under the same curve, f, between b and c. So this. Except for that little spiky part I accidentally got. That third integral says, well, just find the area under f from a all the way to c. Geometry, everything you know about adding together areas, it makes sense that that's true. So if you ever have two integrals, two definite integrals with the same integrand, and the top limit on one is equal to the bottom limit on another one, then you can collapse those two, the sum of those two definite integrals, into one definite integral. So we're going to see some examples next. All right, so these examples are on the back side of the paper that lists all of your rules. So you might like to open your textbook to the list of rules. It might be page 285, somewhere in there. We're practicing these properties so we get used to them. I have some statements of fact up here. These are some truths I've been told. That's what given means, right? I know those statements are true. And I'm going to try to use them, these given statements, plus the properties, to find values for these integrals. This is 5 separate problems. So you're going to have to decide. I'm going to start with the expression I've been asked to evaluate and use the rules to try to come toward that number. You might start with the ones that are given and try to transform them into here. Up to you, it works both ways, but here's what I'm going to do. Letter A says, find the integral from 4 to 1 of f of x dx. So I'm scanning through what's given. This given, which is about h of x, there's no way it can help me, because I'm asked a question about the area under f. I don't even know that h is even related to f. So the only possibilities are these first two that might help me. And so I notice that the second given here, this integral, has the exact same integrand and the exact same limits, but the limits are flipped. So I'm going to use that. Is it rule number 1? Reversing the limits changes the sign. So this expression that I've been given, I know that that's equal to the opposite. I'm moving toward that, but I'm not using that fact yet. It's going to equal the opposite of the same integral, but with the limits switched. And check this out, I have this negative, but this integral, I know its value. Its value is, I crossed out over it, I can't tell. Its value is -2. So I'm going to make a substitution. Everywhere I see this integral, I'm going to replace it with this value. So my answer to letter A is the opposite of -2, which is +2. For letter B, it's a little trickier. Again, this third one's not going to help me because it tells me stuff about H, and then letter B just asks about the area under F. So what can I do here? I want the integral from -1 to 4 of F. Well, notice that that means the area under F between -1 and 4. This is an expression for the area under F between +1 and 4. And this is an expression for the area under F between -1 and 1. So if I think about taking those two areas and squishing them up together next to each other at the place where x equals 1, I'm going to get the area between -1 and 4, which is what I want. So I know that fifth property, the additivity property, it was written to say that if you have two intervals and the two integrals, and the top limit of one equals the bottom limit of the other, then you can take those two and squish them down into 1. Well, here's another way to think about it. I can take one definite integral and I can split it up into two separate parts. Instead of integrating from -1 to 4, I'm going to add together the integral from -1 to 1 and add to that the area under f from 1 to 4. Well, now that I have this new expression, I know what the integral from -1 to 1 of f of x is. It's 5. And then I have this plus sign, and the area under f of x between 1 and 4, I've been told, is -2. Notice this is a 1 and this is a 4, and I check that my limits are in the same order here. I don't have to turn that -2 to its opposite. So I get a final answer, 5 plus -2 makes 3.